Welcome back! We're working through a list of factors that can contribute to the radiative forcing of climate. We just got done talking about the different trace gases that humans add to the atmosphere. Now let's talk about aerosols. This is a tricky word to use if you're not familiar already with it. Aerosols are small, solid, or liquid particles that are suspended in the atmosphere, and they're so small that they don't generally fall. They fall over a very slow period of time. It would take them days to weeks to actually fall all the way through the atmosphere and reach the ground. That doesn't mean they can't be washed out. They can be washed out by precipitation and so on, but actually just falling on their own would be very hard. There's actually a lot of aerosols in the atmosphere. Every cubic centimeter actually has thousands and thousands of them. But most of those are really, really, really super small. Larger particles like dust blowing off the Sahara, as you see in this picture here, might be on the order of a few hundred such particles per cubic centimeter. There's still a lot of them out there, though. Now, the atmosphere has lots of natural sources of aerosols, like dust blowing off the Sahara, or, pollen, or sea salt. When waves break, they splash water. Then when the water evaporates, it leaves salt behind in the atmosphere. There's lots of natural sources of aerosols in the atmosphere. And aerosols are surprisingly important. If you didn't already know, aerosols, these dusts that are in the atmosphere, there's a reason why it's hard to see through dust in the atmosphere. Aerosols interact with both shortwave radiation from the sun and long-wave radiation being emitted by the Earth and so on. And both of those factors can have the potential to affect climate. If the solar radiation can't get through the layer of dust, if the long-wave radiation cannot go through the layer of dust, you have a possible climate forcing. Exactly how any given impact will happen depends rather sensitively on what the aerosols are made of. For example, many fossil fuels contain large amounts of sulfur. I actually planned on having some coal in here just to show you today, and I never figured out where you actually buy coal in the year 2016. But coal contains a large amount of sulfur. It's just a contaminant that's in the coal, and if you burn the coal without doing anything to get rid of the sulfur first, the sulfur ends up in the atmosphere in the form of these little aerosols, and they go through a series of chemical reactions that eventually make what's called sulfate aerosols. They're little droplets of liquid. They're part of the story of acid rain. They're a complicated environmental challenge in general. But these sulfate aerosols have a very high albedo. They're tiny, but each individual one is really good at reflecting shortwave radiation from the sun. And so, we've been burning coal and diesel and natural gas and all kinds of things that have sulfur as a contaminant for about 150 years now. The atmosphere is loaded with this stuff. There's so much of these sulfate aerosols in the atmosphere that they are reflecting some of the shortwave radiation from the sun and keeping it from getting to the surface of the Earth. The Earth is more reflective than it would be if we hadn't been burning this coal all this time. In fact, you can come up, compute based on the size and the chemical composition of sulfate aerosols. It's quite possible to compute the radiative forcing of them, and you get negative 0.4 watts per square meter. It's a negative radiative forcing. In other words, these aerosols are acting to cool the Earth, which isn't terribly surprising. They're reflecting shortwave radiation from the sun before it even gets to the surface of the Earth. Makes sense. Now, anthropogenic sulfur in the atmosphere actually mostly happens down in the lower atmosphere, the troposphere, where, that's where our smokestacks are, that's where our exhaust from our trucks is, etc. And those aerosols are actually pretty easy to wash out of the atmosphere. Sulfate aerosols dissolve easily in water. It's part of the story of acid rain. But, if you burn some coal and sulfur ends up in the atmosphere, it's gone within a few days. All right? This is going to turn out to have implications for how we're going to deal with sulfur and sulfates in the atmosphere and so on. But certainly within a few weeks, that sulfur is washed out. If we stopped burning coal, the atmosphere, the troposphere anyway, would clear itself out from sulfate aerosols pretty fast. But the problem that we're not in control of, though, of course, is volcanoes. Volcanoes spew all kinds of stuff up high into the atmosphere. They get it way up into the stratosphere, and sulfur is one of the more important ones. Here's the deal. Up in the stratosphere, there's no precipitation. Weather doesn't happen in the stratosphere. So there's really no mechanism to wash that sulfate out of the atmosphere when it gets up into the stratosphere, and it can last there for years. In fact, I found this nifty diagram here from This is a particular observatory just keeping track of the transmissivity of the Earth's atmosphere over a period of years. And see how there's 2 periods there where there were big dips in the amount of transmissivity of the Earth's atmosphere? Those are associated with 2 important volcanic eruptions in the last 50 years. One is El Chichon in Mexico, and the other is Mount Pinatubo in the Philippines, that both, knock down the total transmissivity of the Earth's atmosphere by, maybe 10-15% in the days and weeks after the eruption. And you can see, if you look at the shape of that curve there, it took, months to years before the transmissivity of the Earth's atmosphere returned to what it was before. So this tells us something important. It takes a long time to get sulfate out of the stratosphere. It has an important impact in terms of when we're going to start trying to think about solutions to climate change. Gosh, if sulfates are able to reduce the impact of global warming because they have a negative radiative flux, and we can put them up in the stratosphere and they're going to stay there, you can imagine there's some bright money boys out there who are thinking, let's put some sulfate up in the atmosphere. We'll learn the pros and cons of that plan in the 8th module of the course. Alright, so these sulfate aerosols are up there, and they have a very short lifetime in the troposphere, but they have a very long lifetime if they hang out in the stratosphere. Another important aerosol that we put into the atmosphere all the time is black carbon. Black carbon is a really fine, astonishingly fine, actually, black dust. It is very black. That's actually a sample of black carbon right there. And it comes from incomplete combustion of fossil fuels. What do I mean by incomplete combustion? When you burn fossil fuels, we showed you these chemical reactions that showed, how we changed a hydrocarbon into carbon dioxide and water. But that's actually the result of a string of like 4 or 5 chemical reactions that actually happened inside of the pistons of your engine or inside of the coal-fired power plant. If not all of the fossil fuel burns completely, then part of what it comes out of the exhaust of the car or off the smokestack of the power plant is this fine dust called black carbon. And it is very, very black. It has a very low albedo, it absorbs a lot of shortwave radiation, and there's a lot of it out there. Again, we burn fossil fuels by the gigaton. Even if just a tiny bit of it ends up in the form of black carbon, every breath of air you take is loaded with black carbon. Okay, there are particles of black carbon in the air you just breathed in. All right, and it absorbs shortwave radiation. Radiation that hits those shortwave radiation from the sun that hits it is absorbed. That is a warming of the Earth's climate. And in fact, it is a radiative forcing. It can be worked out. It works out to a positive radiative forcing of about 0.2 watts per square meter. So the black carbon that's coming out of like a smokestack is actually contributing to the planet getting warmer. How about mineral dust? Mineral dust is kind of just the dust that comes off the ground. Blowing sand. Sand doesn't really blow. The dust that blows, though, off of a desert, off of a dry lake bed, poorly managed soils in a field where like the farmer has plowed too much and the wind blows the dust, etc. Mineral dust is very reflective stuff. It primarily reflects shortwave radiation from the sun, and as a consequence, it has a net effect of cooling the planet. The radiative forcing of mineral dust planet-wide averages out to about 0.1 watts per square meter. And it can be natural, but about 20% of it comes from anthropogenic sources. Now, we don't have anything that literally just like spews mineral dust into the atmosphere. When we say from anthropogenic sources, we're primarily talking about like poor agricultural practices, plowing the fields too much, draining a lake, things like that. Things that produce a friable, dusty material that then gets blown away. If you add up all the aerosols in the atmosphere and just figure out what is their total direct radiative effect, the total net effect of aerosols is actually to cool the planet. They are better at reflecting shortwave radiation away from the planet than they are at absorbing it or how they interact with long-wave radiation or anything like that. And the net effect is that they have a radiative forcing of about negative 0.5 watts per square meter. That's, considering the whole energy balance of the Earth is only off by 0.6 to 0.9, a whole lot of good is being done by this the radiative forcing of these aerosols. That's actually a thing in climate science. That's called global dimming, and I just shot you here the Wikipedia page about global dimming. Global dimming is this idea that there's aerosols in the atmosphere that are reflecting radiation from the sun before it even gets to the surface of the Earth. And this radiation from the sun is then not warming the surface of the Earth and kind of doing us a favor. It is keeping shortwave radiation from the sun from getting to the surface of the Earth. We are not warming as much as we would if the atmosphere didn't have all those aerosols. We're going to have to think about what that all means for us in a little bit. Now, everything that I've talked about so far has been what we call the aerosol direct effect. It is their direct radiative forcing. How does the aerosol itself absorb or reflect or transmit radiation? Aerosols also have what's called the indirect radiative effect, and that is how the aerosols themselves change the clouds, because clouds then will have an effect on the radiation budget of the Earth. And, well, okay, if we're going to have so this is kind of an indirect effect. See, the aerosols themselves, these tiny little pieces of dust and stuff in the atmosphere, each one serves as what in ATS 113 you'll learn is called a cloud condensation nucleus. Little drops of water form on these tiny aerosols in the atmosphere. And if you change the number of aerosols, you change the distribution of how big the droplets are, how many of them there are inside of a cloud. It still just looks like a cloud, but when you add more aerosols, you get more drops that are tiny. Instead of cleaner air gives you fewer drops that are bigger. You get a few big drops in unpolluted air. You get lots of teensy tiny drops in polluted air, and the size of the droplets in a cloud have a lot to do with its radiative properties. Clouds that contain a lot of tiny drops have a much higher albedo than clouds that are made up of fewer but bigger drops. And the classic example of this is what is called ship tracks. Here I have a satellite picture. There's nothing fancy here. This is literally what an astronaut would have seen looking down on a cloud deck. You see all those lines there? Each one of those lines is where a ship burning diesel sailed under this deck of clouds. Now, the diesel contains sulfur. The sulfate aerosols got up into the atmosphere and got up into these clouds and changed the clouds from having a few big drops and having a comparatively low albedo to having tons of tiny drops and having a much higher albedo. So what you see there, those white lines, that's cloud. Okay, you're not seeing the pollutants. You're seeing the fact that the cloud has a very different effect with regard to shortwave radiation. It now reflects a lot more shortwave radiation than it did before. And this is not something like, oh, this is one special day here. Any given day, you pull up satellite pictures and start looking over the oceans, you can see where ships have sailed under the clouds. That's amazing. You can easily see the changes in reflectivity of these clouds. But keep in mind, those sulfate aerosols are everywhere. They're not just in those. All the clouds are brighter than they would have been if it weren't for the sulfate aerosols. And so as a consequence, overall, clouds are whiter than they were before there was anthropogenic climate change. That's not the only indirect effect aerosols have on clouds. Clouds, the cloud physics is incredibly complicated in terms of how fast it produces precipitation, how high the cloud will grow, whether the cloud contains, what the ratio of ice to liquid in the cloud is, and so on. And all of those change the way the cloud interacts with radiation, and so all of them are included in the total aerosol indirect effect. So the direct effect was cooling at a rate of about 0.5 watts per square meter. That's literally how much radiation is reflected away by the aerosols themselves. And the indirect, how the aerosols change the clouds, is a net effect of negative 0.7 watts per square meter, because the clouds are whiter and they are reflecting more shortwave radiation away from the surface of the Earth. So the total aerosol effect is negative 0.2 watts per square meter. Well, that's nothing to sneeze about. Altogether, our greenhouse gases were adding about plus 3.0 watts per square meter. So these aerosols really are doing us some good. These aerosols are, knocking down, the total radiative forcing on the planet by about 40%. Okay? That's good. They're partly keeping global warming in check, but keep in mind, they are air pollution. Okay? These aerosols that are from anthropogenic sources they are a significant health problem. Okay? They could trigger asthma and so on. We are working very hard to reduce our emissions of these aerosols. When, that's what power plants do, is they add scrubbers and so on to the smokestacks that remove the particulate matter. When they say we've reduced emissions, that's what they're talking about. They're reducing the emissions of these aerosols from the smokestack. But the aerosols were actually kind of doing us good. In fact, a big problem is the fact that China and India, in general, don't have environmental regulations to control the amount of these particulate emissions that a coal plant will have or whatever. And so they're emitting tons of these aerosols, which frankly are kind of doing some good for regard to global climate. Forgetting, of course, about the whole health problems of people in China and India when they breathe this stuff. So as China and India do things to get greener in the coming years, we actually have a new problem. Because now, as we clean out these aerosols from the atmosphere, something that is checking global warming isn't going to be there anymore, at least not as much. Since the lifetime of most aerosols is pretty short, since most aerosols are pretty easy to get washed out of the atmosphere, most of the aerosols are actually found near their sources. Now, on this plot here, I'm showing you the amount of aerosol in the atmosphere. Blue is very little and red is quite a lot. There's reasons why from satellite they can't determine the aerosol over deserts. That's why some places are white, same with over ice fields. And don't worry about the units here or anything like that. This is actually in a quantity called aerosol optical depth. We don't need to worry about that. But if you look for where is all the red in this diagram here, well, one is biomass burning, principally in Africa and in India, where a large amount of burning of, as we clear rainforests and burn the biomass and so on, also charcoal fires and things like that, that's producing enormous burdens of aerosol in the Earth's atmosphere. If you take a look here, there's that mineral dust blown off the Sahara. See how over the ocean there's that big area right off West Africa where there's a lot of dust? That is just easterly winds from the east taking dust off the Sahara and putting it over the ocean. That's an important source of mineral dust in the atmosphere. There's also lots of sources of mineral dust in East Asia. This is a whole soup of different reasons, from bad land practices to dirty power plants to high populations in cities and so on, all of which are contributing to a very large burden of aerosols in the Earth's atmosphere. Now, before we move on to more ways in which we could be affecting the radiative forcing of the Earth, let's just answer a couple quick questions here. Question 6. Burning coal. Burning coal can release blank into the atmosphere. Carbon dioxide, black carbon, sulfur, or all of these. Choose from one of those 4 and get a little feedback before you move on to question 7.